The Elitzur-Vaidman Interaction Free Measurement explained through the theory of entropicity. The Elitzur-Vaidman Interaction Free Measurement, EV-IFM, is one of those quantum results that feels almost magical the first time you hear it. It claims you can detect an object so sensitive that a single photon would trigger it, without ever letting a photon touch it. No explosion, no contact, yet the object is revealed. It sounds impossible until you look at it through the entropic lens of the theory of entropicity, ToE. Within that framework, the effect becomes not only intuitive but expected. What EV Interaction Free Measurement actually demonstrates. The original EV thought experiment imagines a device that would explode if even one photon hits it. You send a photon into an interferometer where it can take two paths at once. If both paths are open, the photon interferes with itself and always exits through a specific port. But if the explosive object blocks one path, even if the photon never goes down that path, the interference disappears. Suddenly, the photon has a chance of showing up in the wrong port. That unexpected detection tells you the object is there. The key insight: the photon does not need to touch the object. The possibility of interaction is enough to change the outcome. Quantum mechanics allows systems to explore multiple potential histories simultaneously. When one of those histories becomes impossible, the entire pattern of outcomes shifts. How the theory of entropicity makes this intuitive. The theory of entropicity reframes quantum behavior in terms of entropic potentiality, the landscape of all possible histories a system can take before any specific history becomes distinguishable. In ToE, three principles matter here. 1. A quantum system does not carry a single definite history until it crosses the entropic threshold of distinguishability. Before that threshold, the system exists as a structured ensemble of potential histories, each weighted by its entropic contribution. 2. The presence of an object reshapes the entropic landscape, even without physical interaction. The object blocks one of the potential histories. That blockage changes the curvature of the entropic field that governs how the system evolves. 3. The photon responds to the entropic field, not just to physical collisions. When the object removes one possible history, the entropic configuration shifts. The interference pattern collapses because the system space of allowable histories has changed. From the ToE perspective, nothing mysterious happens. The object modifies the entropic field. The entropic field modifies the set of possible photon histories. The photon's behavior reflects that modification. The photon does not need to hit the object. The possibility of hitting it is enough to alter the entropic structure of the system. This is why interaction-free measurement works. The measurement is not interaction-free in the entropic sense, it is contact-free. The entropic field still registers the object's presence. Why this removes the spookiness. Traditional quantum explanations often lean on wave-particle duality or superposition as if they were strange exceptions to classical intuition. ToE instead treats quantum behavior as the natural expression of how entropic potentiality organizes itself. Under ToE, EV-IFM is not a paradox. It is not a loophole in quantum mechanics. It is simply the entropic field revealing that one branch of potential history has been removed. The system knows the object is there because the entropic landscape has changed. The photon's path probabilities shift accordingly. This is the same logic that ToE uses to explain other quantum phenomena, delayed choice experiments, quantum erasers, and even gravitational entropic effects, because all of them hinge on how potential histories are shaped, constrained, or eliminated. Why EV-IFM is a window into entropic reality. To appreciate why the theory of entropicity makes interaction-free measurement feel natural rather than paradoxical, it helps to look more closely at what potential histories really mean in an entropic framework. In classical physics, a system has one history. A particle travels along one path, interacts or doesn't interact, and the world proceeds accordingly. But quantum systems do not commit to a single history until the moment the system becomes distinguishable. Before that moment, the system occupies a structured space of possibilities. These possibilities are not vague or mystical. They are mathematically real components of the entropic field. In ToE, this field is not a metaphor. It is the underlying informational entropic structure that determines how physical systems evolve. Every potential history contributes to the curvature of this field. When a new constraint appears, such as an object blocking one of the paths, the curvature changes and the system reorganizes its allowable histories. This is exactly what happens in EV-IFM, the entropic threshold of distinguishability. A central idea in ToE is the entropic threshold of distinguishability. This threshold marks the point at which a system's potential histories become sufficiently different that the universe must choose one of them. Before the threshold, the system evolves as a coherent ensemble of possibilities. After the threshold, the system collapses into a single realized history. In EV-IFM, the explosive object introduces a new constraint. One of the potential histories now leads to an irreversible macroscopic event, an explosion. That history becomes entropically distinct from the others. Even if the photon never travels down that path, the mere presence of a high-entropy outcome reshapes the entropic field. The system crosses the threshold of distinguishability not because of an actual interaction, but because of the entropic weight of a possible interaction. This is why the interference disappears. The entropic field no longer supports a coherent superposition of histories. One of the histories has become too entropically costly to coexist with the others. Why possibility matters more than contact. One of the most counterintuitive aspects of quantum mechanics is that the possibility of an event can influence outcomes even when the event does not occur. ToE explains this cleanly. The entropic field encodes not only what happens but what could happen. The field is shaped by the structure of potentiality, not just by realized events. In EV-IFM, the photon does not need to hit the object. The object's presence removes one potential history. Removing that history changes the entropic curvature. The photon's behavior shifts accordingly. This is not spooky action. It is simply the system responding to a new entropic configuration. The entropic field is sensitive to constraints, boundaries, and forbidden histories. When a path becomes forbidden, the field reorganizes itself. The photon's behavior is just the visible trace of that reorganization. The broader implications for quantum reality. EV-IFM is often presented as a quirky quantum trick, but not through ToE.